All right, hi. Sorry, my name is Megan and I am the team leader from Monash HPR. I'm just going to give a little bit of background as to who we are. So HPR is a very, very new student team. We began about 9 months ago with the aim of entering the Australian University Rocketry Competition, which was the first Australian national competition ever to be run. This presented a lot of unique challenges, which LEAP assisted us with greatly, in that we started in a position where we had to go through large certification processes. We had to launch a large number of rockets before we even got to anything competition standard. This meant that we had to do analysis on a lot of things that we weren't familiar with, and we also had to learn all of our ANSYS techniques and apply them in about, month or 2 month time span. So that was very interesting for us. We began in October with ANSYS Fluent and Mechanical, and we were able to apply some of those learnings to our design phase. And later on in January, after our first major avionics failure from a large-scale test, we actually also adopted the use of HFSS. So given that our rocket experiences about 8 kilonewtons of thrust loading during its launch and also goes up to about 25 Gs of acceleration, we had a lot of very unique and very difficult loading conditions that we had to deal with. In the early stages, we were able to use ANSYS to simulate epoxy adhesion on our bulkheads, as well as to analyse the bulkheads themselves and the payload chamber. So these were designed with ANSYS verifying that they were structurally sound. Later on, as we got further into our design process and learnt how to use composite FEA, we were able to use that to analyse the structural integrity of our composite tubes. This was incredibly important as we were able to identify that they were not sufficient for flight and were able to reinforce them, so when we went to competition we didn't end up with any structural failures, which was a fantastic result. CFD was used not just for design, but actually for trajectory simulation. The scope of our competition is that we are supposed to be as accurate to an altitude as possible, and given that we have no active systems on board, we were relying on making sure that our simulations were as accurate as possible. So a team set about building a custom 6 degree of freedom simulator, which we named Saturn, and this simulator required all kinds of aerodynamic forces and moments that were applied on the rocket across a wide range of flight. So the team had to discretize the flights of our rockets into about 450 different conditions, varying pitch and roll and speeds across both subsonic, transonic and hypersonic speeds. This was incredibly valuable as we actually ended up developing a simulator that was able to analyse our rocket to within 0.1% of simulated altitude, so it was a fantastic result for us, and we hope to use this simulator moving forward also to help us with our active controls. Later on, when we identified that we were actually having major interference problems in our avionics bay, we turned to LEAP in a bit of a stressful situation, asking them to assist us with our shielding. So we realised that there were different things that we could do to help with our shielding from our basic understanding of RF. However, we went to them with a few solutions and identified that some of the ones we believed would be successful actually worsened our problems. So in working with them, we were able to identify what we could do to make sure we were not having any problems with our altimeters. And the figures you see on the screen are basically our avionics configuration with mild changes in the shielding. And you can see we had a very large change in our gain. I think the number I got given was the field interference strength was reduced by about 100 a factor of 100, which is a huge change for us. And this was incredibly, incredibly successful as we actually maintained all of our telemetry all the way up to 30,000 feet. So we got packets all the way up from our RF, which was fantastic. So yet for us, major competition outcomes were that we had no structural failures, which was highly unanticipated. We were experiencing flight loading from the most powerful motor you can really get in Australia. We had a successful simulated altitude and we had no interference issues with our avionics bay. In addition to this, a big part of the competition was actually submitting our analysis to the judges for assessment, and with the assistance of LEAP doing it more than what was required with the HFSS on board, we actually received over 100% in this category. And our flight score, despite not being the second best flight score, actually was improved by the simulation score so much that we came in second place. So we owe a lot of our results to the incredible simulation work that the team was able to do in what was an insanely short amount of time. So massive thank you to David and the team at LEAP.
So, like this? Yep. Thank you, Megan. So I'm Donovan. I'll be speaking for Monash Motorsports. So I'm an aerodynamics engineer, and I'll be talking briefly about what we do, who we are, and how we work together with LEAP to achieve our goals. So briefly, we are a student-run team that design, build, test, and race our very own Formula race cars globally. And we employ students from all different faculties, from design, law, engineering, science, commerce. And we all work together in the technical side, business side, and the management aspects of the team. And the Formula SAE competition we take part in is the largest student engineering competition with around 630 teams across 45 countries across the year in 11 competitions. So just a brief history of the cars. As you can see, like it started out in 2000 with a very simple design. And as we moved on to more aerodynamic packages, as you can see, they were started out really simple with 2D element shapes. And 2013 was when LEAP Australia started working together with us, and that's when the aerodynamic packages started taking the next leap forward with more 3D elements. And after 4 years of working with LEAP, in 2017, we felt confident enough in our aerodynamic packages to actually make 2 cars simultaneously in the same year. One of them is combustion, the other one's fully electric. And that brought us to last year, 2018. So with a full 3D element system of the packages running 2 cars. So briefly in the more technical aspects of what we do at Monash Motorsports. So we do CFD analysis to design the aerodynamic packages. As you can see here, this is just a vorticity to see where the airflow is going around the car to manage it. Obviously, within the design itself, we go through multiple aerodynamic packages, so you can see the iterations as we go through our designs. And we have a standardized reporting system for all of our design reports, which obviously includes the pressure contours and the vectors and the pressure sweeps across the front wheel. So just really quickly, just a short video of what we do. Oh no. There we go. So this is just the total pressure sweep in the x-axis from the front of the car to the rear. So this is just a standard video that's output for every single one of our run that's scripted, obviously with the help from LEAP. There we go. No, that's fine. I'll just continue from here. Let's try this now. Yep. So in 2018, obviously, what's this? Yeah, I'm going to give up. That's fine. So as I scrape the surface of what we do at Monash Motorsports, one of the most important things to remember is that we are a student-run team, which means every year we take a new intake of around 60 to 80 new recruits. And every year, seniors graduate, and with them, they take away the experience and knowledge that they've gained on the team. So the most important thing for the team and our biggest focus is knowledge transfer. And that is where LEAP comes in the most, because it supports us with training and teaching us the required skills we need for us to ensure that we perform at a higher level. And because of that, because of the support from LEAP, last year we managed to get 2nd in the world for the combustion car and 7th for the electric. So feel free to have a chat with us if you have any questions during the break. We're both here. Thank you.